Welcome back to Applied Mathematics. In this video, I want to talk about the graphs of a function. First thing, we've seen previously that functions are a very general idea. So I do want to limit that in this video, I'm going to specifically be talking about real-valued functions. That is, functions where the input, the domain values, are all real numbers, and the output, the range values, are also all real numbers. I have no idea what it would look like to try to graph a function where the inputs are letters and the outputs are colors, so we're just going to ignore that those are things that could exist. With that in mind, the graph of the function f is the graph of y equals f of x. If the function is defined as a table of values, this is going to give us a whole bunch of ordered pairs that we can plot. If the function is defined algebraically, then this is going to give us an equation. So for example, if we are looking at f of x equals 2x squared plus 3x minus 5, then if we want to graph this function, then we want to graph y equals 2x squared plus 3x minus 5. This particular function is defined algebraically. It is what we call a continuous function. It doesn't have any weird things that go wrong. So we know that the graph is going to have infinitely many different points. Graphing infinitely many different points is incredibly challenging, and I'd rather not. So instead, let's just try to break this down a little bit. And in order to graph this function, I am going to start by creating a table of values. I'll label it as x and y. You could also label it as x and f of x. Either one is the same as far as the graph is concerned. And here we take advantage of one of the properties of functions. Every domain value is linked to exactly one range value. So if we pick values for x, we know that each one, we can plug that value in and we'll get exactly one number back out. And that gives us a nice, easy way of setting this up. We don't have to worry about whether there's going to be multiple values. We don't have to worry about whether it's going to be undefined. We can just pick whatever is convenient. Generally, if I'm picking values at random and I know nothing else about the function, I'm just going to pick some symmetric values centered near the origin, -2, -1, 0, 1, and 2. And then for each of these, just plug in. 2 times -2 squared plus 3 times -2 minus 5. You can use a calculator for this. I'm going to kind of mostly do it by hand. So that's going to be 2 minus 5 is -3. It's always a good idea whenever you are using a calculator to at least write out what you're going to plug into the calculator, so that if something goes wrong, it becomes clear that it's a calculator error and not a I don't know what I'm doing kind of error. But we can work through these one by one. I don't have enough space to write all of them out, but I get that f of -2 is -3, f of -1 is -6, f of 0 is -5, f of 1 is 0, and f of 2 is 9. And with just that, we have enough information to sketch a graph. I'll have to be a little bit careful here because there's some fairly large numbers on this graph. So we have to get down to -6 and up to 9. depending on your screen, you may or may not be able to see the graph paper that I'm writing on, but you should be able to see my tick marks. I've marked every other space on the graph paper, and I've counted by twos, which is really each square is 1. I count by twos just so it's a little bit easier to read my labels. But the other thing that I want to point out here is that the x and y axes don't always have to have the same scale. And in fact, in a lot of places, in a lot of applications, having the same scale is kind of nonsensical. So you'll notice that on the vertical direction, every square is 1. On the horizontal direction, on the x-axis, every 2 squares is 1, and that's perfectly fine. It allows us to fit things into the screen a little bit nicer. Then I'm going to plot my points. -2, -3 is right here. -1, -6 is here. 0, -5. 1, 0. And 2, 9. And that gives us something resembling our points. Let's try getting a little bit of a nicer line here. Yeah, we'll just, if you squint and tilt your head, you can pretend that that line goes through all the points nicely. I never claimed to be a good artist, and this is a lot of why having the list of points and having the points actually drawn is so useful. Before I move on, I do want to point out one thing. I kind of regret where I drew this, because if I put my head back on the screen and tried to gesture, you would not see any of the graph anymore. But I want to point out that my graph continues beyond the points that I plotted, right? I plotted a couple of points in the middle. The graph continues beyond that, and I made sure to draw the line continuing beyond that. And I drew arrowheads on both ends of the line to indicate that the graph keeps going beyond what fits on my screen. These are all things that are very important to understanding a graph. They're little things, they're easy to forget, they're easy to look over, but they do actually make a difference. Just as a really quick example, if I'm looking at the function y equals the square root of x, all right, so square root is my function, nothing else crazy going on here. This is an interesting one because the square root has a restricted domain, right? There are negative values of x are nonsensical. So when I'm picking values for x, I have to think about picking positive numbers. I can't pick negative numbers. And if I'm thinking very carefully about things, I don't have to pick 1, 2, 3. I can pick some numbers that are very convenient. I know I have to take the square roots of all of these numbers. I might as well take numbers that have nice square roots. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. When I sketch this graph, here I have to do things a little bit differently. I can plot my points just the same, 0, 0, 1, 1, 4, 2, 9, 3, and when I draw my curve this time, to the right it continues forever, but to the left it does not, because the function is not defined for negative values of x. So the graph stops there. That's why when the graph doesn't stop, when the function doesn't stop, it's so important to draw those arrows, because when it does, it's important to indicate. Now that we have the tool of graphing functions at our disposal, we can look at things in the other direction. It is actually possible to define a function by its graph. If I draw a curve that looks like this, what is this curve? I have no idea. It doesn't matter. What matters is that I can draw it, and I can use the drawing as a way of approximating the value of the function. So if I name this curve f of x, and I ask you to evaluate f of 3, well, when I go to x equals 3 and I come up, very conveniently there's a point given right there, which comes out at 2. So I know that f of 3, come on, equals 2. If I give a point that is a little bit harder to deal with, f of, say, 1.7, well, 1.7 is somewhere in the general vicinity of here. And when I come up, it hits my function around about there. And when I come over, it's, well, somewhere in the vicinity of there. I don't know, that looks to me something like 0.3. It's not a precise value, but it is a value. And by looking at the graph, we can read these values. And in that sense, this graph fully defines the function. Now, which way do we want to look at this? Are we using the graph as a tool for analyzing the function or defining the function? Depends on the application of the problem. In either sense, we have a very simple tool for analysis. The vertical line test is our way of answering the question, is this actually a function? Remember that the definition of a function says that for every element in the domain, there is exactly one corresponding element in the range. And remember that the domain is the thing that we've been calling x, and the range is the thing we've been calling y. So if we think about the coordinate plane, if we pick a value for x, all of the points on the coordinate plane that have the same value of x fall on a vertical line. Right? Any equation in the form x equals c is the graph of a vertical line. The value, if I have a function here, the value at the point where these things intersect is f of c. If you have a curve like an oval, and you try to draw that vertical line in, well, that vertical line crosses the graph in more than one place. And because that vertical line crosses the graph in more than one place, we don't have a clear answer for what is the value of the function at this point. So we know that this curve, while it could be an interesting curve, it is not a function. And the tools that we have for working with functions won't work or won't work immediately without having to do some sort of modification. The formal statement of the vertical line test usually says something like, no vertical line is able to intersect the graph of a function more than once. The practical use generally turns that on its head. If there is at least one vertical line which intersects a graph more than once, then the graph is not a function. And that's something that is very often overlooked or misunderstood or misrepresented by instructors. The vertical line test cannot tell us for certain that a graph is a function. It can tell us for certain that a graph is not a function. If I sketch out one more graph here real quick. And I come up with something that looks like this. This absolutely looks like a function. It passes the vertical line test. But it's also a window. We are only seeing a small portion of the curve that is this graph. It continues onward indefinitely. It is considered misleading, not quite so far as wrong, but very misleading, to choose a window to display a graph where anything interesting happens outside of the window. So generally speaking, when you're looking at a graph like this, the expectation is that the graph is just going to continue doing the same thing it was doing indefinitely, just straight lines or closer and closer to straight lines, without anything funny happening. But what if it did that? We can't see the part in blue because it's all happening outside of the coordinate axes that I drew. It is off of the window of where we're looking. And there is something very strange happening there, which definitely makes this not a function. I will assure you that I never want to trick you, and no reasonable person would ever want to trick you by asking you whether this graph is a function and then hiding all of the interesting stuff going on off here. But it illustrates the point. This graph looks like a function. This graph could be a function. We have to hedge our bets, and we can't say certainly this graph is a function. All right. Last thing I want to talk about in this video is computer software. Here I am at Desmos, and I've shuffled this course around a couple of times, so I'm not sure whether I've used Desmos previously or not. Desmos is a free web-based graphing software. You can type in an equation. Here you can see over here, I've typed in the function we were looking at earlier, f of x equals 2x squared plus 3x minus 5. And with just that information, Desmos is able to produce the graph. A couple of other things I want to point out up here above my head. There's this button here for Share Graph, and it has a way to export the image or print it so that you can provide it as part of an assignment or continue working pencil and paper from there. I also want to point out that wrench-looking thing above my head. I get my head out of the way so you can see what pops up. This allows you to specify the window. Where are the upper and lower extents of the x and y axis? There's a bunch of other stuff it does as well that I don't really care that much about. Or we can just take the simple zoom in and zoom out. I'll also point out that if I click and drag, I can move this around. And if I use my mouse wheel, I can scroll in and out as well. and there is a home button if you've done anything a little bit too strange that will take you back to a default zoom. So we can look at the graph of a function without having to do much of any work. The computer does all the work for us. Well, why then did I bother telling you how to graph a function by hand? Well, in part because you're going to be taking exams in this course where you aren't going to have access to Desmos, so there is a very practical course reason that is completely useless in the, well, that's an artificial restriction. But beyond that, understanding how the graph of a function is developed, understanding what we really mean when we're looking at the graph of a function, I think is more important than being able to produce the graph of a function. Because right now, yay, it's a picture, I guess. I guess that's helpful. As you continue on in your mathematics education, and especially as you go into the applied mathematical sciences, you'll start learning more and more tools for how to analyze a graph, how to look for interesting features of a graph and relate them to a problem at hand. There are too many options to choose from right now. There's no very clear, this is something everyone should know kind of example I can use. So we're kind of sidestepping that question a little bit for right now, which is, I'm sure, very disappointing for you. It's disappointing for me as well. But this is a tool. How you use the tool is going to be something you see as you move onward. But for right now, we have the tool, and that's interesting in and of itself. The last thing that I want to talk about in Desmos, over here, above where I've set this up, there's a gear over there. When I hover over that, it says Edit List, and it gives me a couple of options. It lets me get rid of these things. If I click on the button over here, it will let me change the color of the graph. I take a lot of advantage of that because I'm colorblind and some of those colors don't actually look different to me. But the thing that I want to point out is the Create Table button, which is going to give us this table of values. And you'll recognize that that's exactly the data points that we had figured out earlier. And I'll just point out that if I fill in another x value on the table, it will insert that next row. It will calculate what the value is supposed to be. And we don't have to stick with nice whole numbers. I can plug in, say, x equals 2.5 to get out, what is that, 15. So we have options at our disposal. Desmos is able to do a lot of work. We're just scratching the surface of what it's capable of. But I've been going on long enough, so I think I'm going to wrap this video up here. As always, thank you for joining me, and I'll see you next time.